And then I have the pleasure to introduce Joel here, Joel Levine, who studies atmospheres of Earth and Mars and the evolution and all the things we need to know about it. And his panel is going to discuss, actually our knowledge gaps, I think, in what we need to know before we put humans on Mars, the nitty-gritty details of how to do that. And we need to know, right, if we want to go. The floor is yours.
Thank you, thank you, thank you. It's certainly a pleasure to be back here. I was here last year. It was a fantastic meeting, and this looks like a fantastic meeting too. We've been talking about sending humans to Mars, and one of the things that's very important is that we reduce the risk of a human landing and then a human return. And those are some of the topics that we're going to address. We have a very distinguished panel, and I'll introduce very briefly, because all the bios are online, as you know, I'll very briefly introduce our speakers. Our first speaker is Ellen Stofan, who was appointed NASA Chief Scientist on August 25th, 2013, serving as a principal advisor to the NASA Administrator, Charles Bolden, on agency science programs and science-related strategic planning and investment. Do you know that the Mars community is very lucky to have Dr. Stofan in the position of key scientist at the very time important decisions are being made on sending humans to Mars. Dr. Stofan is a world-class geologist. Her research has focused on the geology of Mars, Venus, Titan, and Earth. She's an associate member of the Cassini mission radar team and a co-investigator on the Mars Express sounder, a radar sounder. She was also principal investigator on the Titan Mare Explorer, our proposed mission to send a floating lander to land on a sea on Titan. That was all before she became the chief scientist, and she was one of the 4 runner-ups in that competition. So that's a great achievement. Second speaker, Pascale Ehrenfreund, is a research professor of space policy and international affairs at the Space Policy Institute right here at George Washington University. Since September 2013, she is the president of the Austrian Science Fund. She chairs the panel on exploration for COSPAR, and COSPAR will meet in Russia, and some people may even be allowed to go there if you work for NASA. She is president of International Astronomical Union Commission 51 Bioastronomy. She's a member of the NRC Committee on Human Spaceflight, the NRC Committee on Astrobiology and Planetary Science, and about a dozen other important international committees. Jim Zimbelman is a planetary geologist at the Center for Earth and Planetary Studies at the National Air and Space Museum at the Smithsonian. He's been a research geologist there since 1988. He conducts research related to volcanic and wind surface interaction processes and landform processes on Earth and the terrestrial planets, particularly Mars, and in the preparation of geological maps of Mars and Venus. Last year, Jim was awarded the 2013 Ron Greeley Award for Distinguished Service by the Planetary Geology Division of GSA. So without any further introduction, let me start with NASA's Chief Scientist, Ellen Stofan. Ellen?
Okay. You've been hearing, that is working, okay. You've been hearing for the last few days about why Mars and about how Mars, and even more importantly, how soon. But as has been discussed throughout this meeting, the science is a critical part of all of this. It's a key part of why we're going, and it's a key part of how we're going to get there. And there are science measurements left that we need to make, which you'll be hearing about in detail in this session. These are covered in something called the strategic knowledge gaps, which were first developed by Dr. Mike Wargo, which help govern the work that we need to do here on the ground, in laboratories, and at Mars. So a lot of this work, again, needs to take place here on the ground, as well as what we need to do actually at Mars. Now, somehow somebody told me I'd have a clicker, which I do not have. There it is. Thanks. Okay. Okay. The scientific path to Mars is familiar to most of you, and it follows the simple scientific method, building on each discovery as we go. We knew from early on, you know, if you even want to go back all the way to the discovery of Canale, that it was all going to be about the water. But as time has gone on and technologies have improved, our ability to address more sophisticated questions has come about. Odyssey, MRO, Mars Express have made the geochemical measurements, looking for things like clay minerals, that have allowed us to select better and better landing sites, along with all the visible data that we have from, again, a huge list of missions that give us clues to past water-rich environments. Exploration by rovers has laid the stage by identifying ever more habitable environments, with Curiosity identifying the most stable, possibly habitable place yet that we have visited. And I think we can be prepared. I know Melissa Traynor was here yesterday, but we can be prepared for future measurements by SAM. I know they just selected a new a drilling site that I think are really going to get us excited about that potential of the Mount Sharp region as a potentially habitable area. MAVEN, which is up on the list and on its way to Mars, is going to be giving us important clues again to this history. What is the history of water on Mars? In MAVEN's case, focusing on water loss processes. And InSight is going to give us better idea of the interior evolution, the interior structure of Mars. And it's really important that we attack all these aspects of Mars, from the interior to the surface, all the way to the top of the atmosphere, because planets are complex systems. And if you're trying to understand something like the water cycle, when was water stable, how long did it last on the surface, we really need to understand Mars from all of its aspects, again, all the way from the core to the top of the atmosphere, to the interactions of that atmosphere with the solar wind. So to understand habitability, to better define where and for how long and when liquid water was stable at the surface, we need to attack all the pieces of the planetary puzzle. The sites that we've explored, from Curiosity to Opportunity to Spirit, back to Pathfinder, and all the way back to Viking, have allowed us to understand how to be Martians, how to operate and live on the surface of Mars. And obviously we've seen quite a varied sites, as you can see from up here, always dominated, of course, by that wonderful dust that covers the surface of Mars, but also a variety of rock conditions, dunes, dust that's so thick you can get your rover stuck in it. So a whole range of conditions. We've really been learning. When you think about the fact we've now landed successfully on Mars 7 times, we've been able to explore mobily a bunch of those sites, and we've really started to learn how to work on Mars. These landing sites, and again, along with the Phoenix landing site, get us on the way to help fill these strategic knowledge gaps, giving us the basic data to start addressing them. Landing site characterization, things like hazards, regolith physical properties and structure, surface trafficability, and our ability to select safe landing sites based on orbital data. And I would argue we've actually gotten pretty good at this. We've landed in a variety of settings. We've been able to pick extremely interesting geologic settings. Again, this follow the water, our orbital data that we've gathered from this whole flotilla of spacecraft that we've had in orbit around Mars. Those orbital data are really critical to this safe and interesting landing site. Because if it's safe and not interesting, that's not good. And if it's interesting and not safe, that's not good either. And so I think we've been able to demonstrate through our Mars scientific program that we know what to do and where to go. These sites have allowed us to start to poke into an area where we have much left to do, in situ resource potential. And I know you've had a whole session on this yesterday. We want to know what are the hydrated mineral compositions and occurrences, what are the shallow water ice occurrences, what's the composition exactly of that subsurface ice, and what are its properties. There's also obviously atmospheric in situ resource utilization. The dust that's in the atmospheric column above the surface, its physical and chemical and compositional properties and its electrical properties, as well as trace gases that are occurring in the atmosphere. So this whole issue of ISRU is something that I think we're sort of right on the verge of really being able to attack in a meaningful way. We've made some of the measurements we need to make, but not all of them. We've visited some of the sites on Mars that are interesting for this, but certainly not all of them. And we continue to need to make higher and higher resolution, more complete orbital measurements across the wavelength spectrum to help us put our better and better ground truth that we've gotten from our rovers into a global context. For Earth, you know, when we talk about the importance of orbital measurements, a lot of it's about continuity. We need to make sure for Earth observations that we have continuity of the various things that we're measuring about climate and weather. For Mars, I think the really critical continuity that we're going to need is, first of all, we're going to need continuity of a comm system around Mars, a relay system for communications, which is outside the scope of this session. But we're also going to have, again, this ongoing push to have continuous high-resolution coverage across the surface to really help to select, again, safe and interesting future landing sites. And at some point, I'm obviously biased since you heard from my background, but I'd love to see us get a synthetic aperture radar there at some point, which I think will also give us a whole different view of Mars. Curiosity's trip up Mount Sharp is helping us learn more and attack this issue of surface trafficability even more. And I would argue, while we're obviously not happy that there's been damage to the wheels, when you have things like that happen, you really learn a lot more than if everything goes completely right. So we're learning, again, how to operate in difficult conditions, and what's the best way to design surface mobility on Mars. Curiosity has also given us the ability, which certainly some of us hoped for but was never explicitly said. It's also allowed us to do the first ever age dates on the surface of Mars. And to a geologist, that's just a gigantic, huge, big deal. Because it takes our ability to say, well, we think this, based on the crater population, we think this type of unit or these habitable conditions on Mars may have existed in sort of this time frame. Surface age dating, which the SAM instrument and another instrument on Curiosity has been able to demonstrate, can really tie that down much more specifically. It's giving us exposure ages, which tell us about the activity on the surface, which again goes back to this: how can we really define what's a habitable environment and get back and make the measurements that we need to make. But Curiosity has also helped us to better address the strategic knowledge gaps of environmental and radiation effects, dust effects, and potential toxicity to human health, which we were just hearing about in the last session. With the RAD instrument, we can now quantify the surface radiation environment for the first time. Mars 2020 will continue these studies as we work together as an agency, science, human exploration, and technology, to create the safe path forward for humans to Mars. And as we think about future landing sites from a pure science perspective, we'll continue to focus as a science community on the characterization, identification of habitable environments. This was one of the sites that made it into sort of the final rounds for the MSL site, but wasn't finally selected. It's a site called Eberswald Crater. It's another crater lake environment, in some ways quite similar to Gale, a crater that was chosen for the MSL landing. It has a river delta system, and again, minerals that are telling you that it's a potentially habitable environment. As we begin to come together as a science community to debate where Mars 2020 will go, you know, we don't know that this is going to be one of the candidates, but we're certainly going to be looking for those same criteria. Can we identify all the different aspects that would indicate possible habitability in the past? But I also think we're beginning now to pivot to also taking into account how we can best utilize whatever site is chosen as part of what I would say is a new era of combined science and human exploration. And it's almost, to me, time to stop talking about it that way. Whether we're scientists on Earth, you know, doing research or operating a rover up on Mars, or at some point we're in situ scientists on the surface of Mars. You know, Bill Gerstenmaier has said, we're pioneering Mars. It's not about human exploration. It's not about scientific exploration. We're really combined into one focus right now, and we've already begun this path to Mars. So future missions really need to be measuring the radiation environment. They need to be characterizing the dust, the properties of the dust, and the availability and potential for in situ resource utilization, no matter what type of mission it is. And of course, some of the most important strategic knowledge gaps are for the atmosphere, and MAVEN will help to address some of them. We obviously need the upper atmosphere global temperature field, aerosol properties, the global winds, wind profiles, orbital particulate environment, and a lot of information about the lower atmosphere, including global surface pressure, local weather, surface winds, and electrification. The EDL profile through the entire atmosphere, but particularly in the lower atmosphere, is critical. And all missions to Mars, again, in the future, are part of this pioneering of Mars. So in all future missions, and this is obviously in the plans for Mars 2020, we need to be collecting this critical EDL information. And so we'll be working, again, the technology side of NASA with science and human exploration to make sure we get the measurements we need on Mars 2020. The combined goal is to get astrobiologists, geologists, and geochemists to the surface of Mars, where we can more efficiently and creatively explore the surface. But again, before we do that, we have to be able to close these strategic knowledge gaps. And I want to emphasize again the importance of not just the measurements we need to make at Mars, but the work we need to do here on Earth. Our research and analysis programs, from mapping Mars to conducting test ISRU experiments, to trying to locate and quantify subsurface ice using the data sets that we have, to lab experiments and tests, to theoretical modeling. All of these things that we're doing are contributing to pioneering Mars. The research and analysis and the technology development, which also can't be forgotten, including instrument development to make these better and better measurements that we need from orbit, are on the critical path. Eventually, we need to start planning beyond Mars 2020, looking at the science from the decadal and combining it with the work we need to do to close these SKGs, and then best utilizing humans to do surface science. So whether as we go forward after Mars 2020, with rovers to explore more potential landing sites, or a sample return mission that can also test, for example, maybe ISRU and orbital rendezvous, in preparation for future missions. I would argue that every single science mission going forward to Mars is part of this pioneering adventure that we've started on. Thank you.
Yeah, good morning. I'm here for the third day, and what I did yesterday, I threw my slides in the recycling bin because I didn't want to be repetitive. So much has been said. It was really a pleasure to see all those presentations on the various topics and also on the strategic knowledge gaps as we have heard it today. So I have changed a little bit and tried to present some things which are which have not been heard, or in particular some of the European adventures and roadmaps and what we are trying to do in Europe. So I think also from this morning and also from the afternoon sessions yesterday, you have seen how integral it is. Ground-based testing, testing on the International Space Station, testing in the field, all this is really crucial in order to obtain the knowledge we need in order to put human on another planet. And I will try to go a little bit through the different aspects which have not been covered so much in the last sessions. And one of them are simulations in the laboratory, where we in particular simulate the stability of organic material, other materials, and also microbes under simulated Mars conditions. This is a worldwide exercise where groups are very well connected in the United States, Europe, Japan, and we exchange those data and try actually to put them into a database. It is important for many aspects, including forward contamination, because also when we go to Mars with humans, we want to behave responsible, we want to be safe, and you will have a session this afternoon, particularly on this topic on planetary protection. It is very crucial that we understand how organisms can live, how they can grow in case on Mars, how organic materials are actually, how stable they are, and how they could eventually affect humans when they land. What is the dust? How are the dust and the organics interacting? And how is this affecting, for instance, spacesuits and the health of human explorers? And there are many, many experiments done all over the world, and I wanted to emphasize how important also the laboratory simulations are in this context. And obviously, we are also doing a lot of experiments, and that's a very beautiful example of European, American, and Russian cooperation, how we actually exploit exposure facilities on the International Space Station. There were many in the last 2 decades, very important results, and Biopan, the ERA facility, and most recently the exposed facilities on the European Columbus, but also on the Russian Zvezda module, and where a lot of experiments from all over the world have been deployed and being exposed for nearly 22 months, one mission, the other one a little bit less, being returned to Earth and analyzed for stability, in particular to radiation and conditions in space. And we have heard it's a bit difficult to simulate or to test galactic cosmic rays on the altitude on the space station, but if you go higher with small satellites, and the last slide here shows you NASA's Orion satellite. We have launched this satellite in 650-kilometer orbit in 2010 and performed really exciting tests on microbes, but also on organic material under space conditions. So there are some interesting results, which this is an experiment which is done in Europe, which I'm involved in, where we, for instance, expose materials in the Concordia station in Antarctica in order to simulate what kind of materials could be used. We are testing antimicrobial coatings on many, many different surfaces, and that will stay, that is actually in Concordia station over a whole year in order to understand how habitats can be made safe on their way to Mars, and also when they are on Mars. So there are many different experiments which are happening actually ground-based. Pascale was not here, unfortunately, today, but there are really a lot of robotic and also for life science experiments which are done in the field. And I want to draw your attention to the UMEC study from the European Commission and the DLR, which is, has been performed in 2003 and published, which really made a very, very thorough analysis on radiation health risks, on microgravity effects, psychological risks, and also for life support systems. It's a very big document which you can download, which has simulated a lunar base, but in particular a 500-day mission on Mars and a 30-day mission on Mars with very, very interesting data. And there are many publications about that. And there is also the Theseus concept, which has been taken up by the European Science Foundation. You have here the website where you can download the roadmap, where Europe actually tried to make an integrated roadmap. We have seen and we have spoken so much in the last days how important it is to pull all this data together in order to make it safe to land humans on Mars. And that's exactly done by different countries in Europe. They have taken a responsibility for one of these topics and have worked together on the topics which you have talked and discussed a lot on this conference, healthcare, habitat management, psychology, radiation, but also how to make an integral approach and how to actually get those data together. And obviously that has also a very important international aspect for the future. And it has been shortly discussed today, and we have is really a very new facility from the German Space Agency, which is open to everybody. It's like a business case. It is for the entire society. It is not only for us space freaks and really working hard on that topic. It is also for the public and for industry in order to interact. It has a short arm human centrifuge. It has laboratories where you can test pressure. It has a sleep laboratory. It has a lot of medical facilities where you can test human health. It is a really, really large 3,500 square meter space habitat, which has been opened recently. And I hope that this is also a facility which will bring people worldwide together really by bringing people together in order to prepare for human exploration on Mars. And my last slide, which has been, I think, not so much discussed on this conference, Mars 500 was a very, very important step. 6 astronauts, 3 Russians, 1 French, 1 Italian, and 1 Chinese. And they have spent a very, very long time in this habitat. Obviously, this habitat was much larger than any habitat they will ever be on Mars, but it was a really good test case where they could test a lot of different aspects, and in particular, human health and microbial situation in the habitat, psychological stress, salt uptake, many, many different aspects. And also what I remember is that they really found that the temperature actually was dropping in the human body temperature was dropping 0.5 degrees over this period. And so there are still after tests done, and I think it is also something which is really shows an international exercise. I want to stop here by saying that I think it is crucial to look at all these preparation tests also worldwide and try to pull them together, not to be redundant, and try to put standards in order to really exploit all this kind of knowledge which has been obtained in the last 2 decades and will be obtained now with recent and new facilities, in order that we are all able together to explore Mars with humans. Thank you.
Good morning. We're going to change theme a little bit here. I'm going to follow on what Ellen discussed with picking sites that are safe and interesting. It's just from my standpoint, and do realize you're going to get the viewpoint of a geologist here in the next few minutes. The engineers tend to want the safe site. The geologists and other scientists tend to want the interesting site. Well, it's a real balancing act, and I hope that in the next few minutes I'll help to convince you that I think NASA has come up with a remarkably robust paradigm for achieving both of those, balancing the needs of both of those. And what we'll do is look at the 5 recent landing sites that Ellen mentioned, but I'm going to again take it from kind of the science perspective and a little bit of planetary forensics. What did we know and when did we know it? Wrong one. Okay? So here's Viking, and believe me, I'm a very strong supporter of the historic importance of Viking, but I want to impress on you how lucky we were with the 2 Vikings. Prior to the arrival of the Viking orbiter and lander at Mars in June of 1976, the information we had was based on Mariner 9. 100 meter per pixel was good, but that was very, very spotty. Our global mapping was more kilometer scale picture elements. Think about that for a minute, what that means you could see on the planet. Radar, we did have radar, but with very large footprints, so that we didn't have very accurate ideas of where that scattering was coming from. Topography, almost unknown. Only from Mariner 9 occultations did we have some clue as to what the relief was on the planet. When Viking Orbiter 1, carrying the lander, went into orbit, they started getting these first Viking 40 meter per pixel images, scared both the engineers and the scientists to death. They saw craters, they saw boulders, they saw all of this stuff in the place that they had picked on the Mariner 9 information to be their primary landing site. In the next 3 weeks, they selected a site several hundred kilometers away. That's remarkable, but in my mind, that is not the way we want to pick landing sites. 3 weeks is not the kind of time frame you need to evaluate this kind of information. And finally, infrared was new, really, on Viking. It could provide very little help in the landing site selection. That has changed dramatically in the coming years. Well, a couple of months after Viking 1, Viking 2 set down, and you're probably all familiar with this curved horizon. Well, I'll remind you the reason that horizon appears curved is because one of the 3 footpads got hung up on many of these rocks that are in the landing site. This site was chosen by the science team saying, we're going to put the second lander down on some rolling sand dunes. Look, that's the rockiest place we have visited yet. But these rocks are well below the resolving capability of the instruments, even on the Viking orbiters. And it turns out we were even more lucky that one of those footpads did get hung up on a block, because there was a mirror on one of the landers that allowed the camera to look underneath Viking 2. There was a very pointy rock with the top only a couple of centimeters from the bottom of the spacecraft. Had we not had this tilted view, we may not have had a successful Viking 2 landing. Okay, this was 1976. Unfortunately, there was a 20-year gap before we landed again. Isn't because of trying, lack of trying. We had a couple of failures in there that really caused NASA to look inward and look at itself and say, what are we not taking care of in making some of these assessments? Came up with Mars Pathfinder, and this name is interesting because the idea was a completely new technology. I still remember hearing, you're going to do what to a spacecraft, surround it with airbags and throw it onto a block of rocks? That's crazy. But it worked. This was the beginning of my conversion to becoming a very strong advocate for how good our engineers have gotten. But I thought this was nuts. Now, unlike Viking, Pathfinder was specifically looking for the rocks. They wanted a rocky site. And interestingly, the site they picked, based on 20 years of Viking information and analyzing that for 20 years, was very close to where Viking 1 should have gone based on the Mariner 9 assessment. That turned out to be one of the rockiest spots on the planet based on what we knew from Mariner 9. Well, the airbags worked wonderfully. We got wonderful rocks, but the real innovation at Pathfinder, obviously, was having Sojourner to give us mobility, a real paradigm shift in how we want to investigate planets. Well, what did we know in preparing for the Pathfinder landing? Pretty good Viking orbital coverage. We had 2 landers giving us information for over years, timescales from the surface. Earth-based radar still gave us slope and roughness information, but topography was improved significantly from the Viking measurements, both occultations and stereo imaging, to give us some relief. However, our uncertainties in that elevation was in the kilometer range. Topographically, our view of Mars at the time of Pathfinder was about as bad geographically as it was with the Mariner 9 information. We knew broadly what was up and down, but again, the absolute values of those were off by kilometers. Infrared came into its own in this time frame. In particular, a scientist, Phil Christensen, came up with a remarkable way of using thermal infrared measurements at multiple wavelengths to infer the abundance of rocks, as in something that emitted a lot of heat energy at these different wavelengths, on a scale much smaller than the measurement of the infrared instrument. His rock maps have turned out to be terribly important for all of our subsequent information. And one final thing about this particular selection, the site had been chosen well before they had a workshop in the channeled scablands at Washington. I think this was a very important way of getting not just the scientists, but the engineers together out at a terrestrial analog for the site they wanted to go to. Walked around and the rocks together and talked about it. I think that helped everyone in the long run. Well, the rovers that we're most familiar with, because one is still going, Opportunity is still doing its own explorations, is an evolution off of the Pathfinder theme. We used airbags again. Well, now we had a lot more information. Mars Global Surveyor, Mars Odyssey. MOC in particular was giving us 1.5 meter per pixel kinds of images, extremely important in evaluating the possible landing sites. Plus, even broader context that is still significantly better than what we had from either Mariner 9 or Viking. Earth-based radar topography was substantially improved by Mars Global Surveyor with MOLA, where we knew in an absolute sense relief to a meter. That completely changed many of our perceptions of the entire planet. Terribly important for planning accurately from an engineering standpoint what site we needed to go to for the constraints of the rovers. Rock maps were still going, but there were new infrared instruments that this technique could be applied to with better resolution, improving our ability to estimate the abundance of rocks even in an area that's smaller than where we were making the thermal measurements. Modeling of what was going on was important. For these landers, they had maximum wind constraints, and that modeling could not have been achieved without some of this other information. And finally, the real shift here was, rather than just a single field workshop, there was a series of landing site workshops where they opened to the community. Anybody could propose. In fact, I proposed a landing site. It didn't last very long, but that's the point. It was essentially peer review applied to a landing site process. Your colleagues, you had to defend to your colleagues, why do you want to go there? And the engineers would say, is it safe? At the same time, a lot of give and take. Went from 155 down to 4 sites that were then passed on to NASA headquarters to make the ultimate choices. Remarkably effective, and I think it got the entire science community on board. These are our sites. These are the places we want to go to. Phoenix, a little bit of change of theme here because it was not a rover. It was sent to the high latitudes, so its goal was a bit different than what we had been discussing. We had even more information coming into play because Mars Reconnaissance Orbiter and Mars Express were both active. We've just got an abundance of data sources available now, supplying not in the infrared, not only the block abundance, but now compositional constraints on possible landing sites, modeling of not only the winds, but where the ground ice should be. And I think Phoenix demonstrated that those models really paid off. Now, maybe some of you have seen this mosaic of images. Here's the footpad of Phoenix sitting on the ground. And the sample arm and all the instruments did, in fact, do what the scientists wanted it to do. But interestingly, the landing rockets in a Viking-style landing on the surface actually blew the soil off of the ground ice that we were looking at. And we didn't realize that until several weeks into the mission, that they had exposed the ground ice that was, in fact, the goal of this science mission through the landing process itself. The engineers helped the scientists. And now, finally, Mars Science Laboratory, and maybe as good as that wonderful model is outside, it makes a difference when I was standing by a model and looking up into the cameras on this rover. This is a big vehicle that we have put onto Mars. The constraints for the selection of this site were it had to be radar reflective because the radar properties were very important in triggering many of the events in the complicated EDL sequence here. Again, a host of information, really not that different from what we had at Phoenix, but now we were looking at sites, again, all over the planet. Started with more than 50, narrowed down to 4 sites that were again passed on to NASA headquarters to make the final selection. I think this kind of approach is not only the way to put rovers on Mars, but it's the way we should at least use as the beginning of thinking of how we're going to assess putting humans onto Mars. Having both the engineers and the scientists together, not for weeks, but for years, debating and discussing, give and take, on what we need to achieve these very important goals.
Okay, before we open to questions, I just wanted to show you 2 reports that you can read at your leisure. All of these charts will be available online, Explore Mars, so you'll be able to get all of these charts. What I want to talk about very briefly is atmospheric dust on Mars. Everyone alluded to atmospheric dust. It's a risk to astronauts, to mechanical systems like habitats and spacesuits, to surface operations, as well as it's a risk to the future human exploration of Mars. There are 2 documents that I want to point out. There have been 2 reports over the last 10 years that describe human safety on Mars. The first is the National Research Council, Safe on Mars, Precursor Measurements Necessary to Support Human Operations on the Martian Surface. As I say, it's an NRC report. Then in 2005, the Mars Exploration Program Analysis Group, MEPEG, had a Mars Human Precursor Science Steering Group, and in 2005 published a paper that's online. You can download it. It's about 77 pages. It's called An Analysis of the Precursor Measurements of Mars Needed to Reduce the Risk of the First Human Mission to Mars. And I think there were about 80 people on that panel, and it makes very, very good reading. And one of the interesting things, as you read it, we have only addressed a very small fraction of those questions. And let me just talk about a major concern. Lunar dust and the Apollo experience. After 3 days, lunar dust contamination on the EVA suit bearings led to such difficulty in movement that another EVA would not have been possible. Dust clinging to the EVA suits was transported into the lunar module. During the return to Earth, when microgravity was reestablished, the dust on the suits became airborne and floated through the entire lunar module cabin. The crews inhaled the dust, and it irritated their eyes, and some mechanical systems aboard the Apollo spacecraft were damaged due to dust contamination. That's all from the MEPEG report where they discuss the lunar experience. And let me point out that Mars is a very, very dusty place. As Ellen said, windblown surface dust is a regular component of the atmosphere of Mars. The dust varies with location, local time, and season, from very small scale dust storms to planetary scale dust storms. We believe the dust on Mars may be highly oxidative and chemically reactive. We know that the surface of Mars is a very highly oxidized surface because of the deposition of hydrogen peroxide, H2O2, and ozone from the atmosphere to the surface. And the wind-blown regolith material may also be very chemically reactive, plus the fact that there may be, this dust may be electrically charged, and enough of it in the atmosphere can lead to a possible lightning discharge. So with that, I would like to conclude the presentation portion of the series and invite the audience to come to the microphones to ask questions or give comments. And if you're asking a question, please identify who you would like to try to answer the question. Yeah. Thank you.
Quick question for Ellen. Is Siding Spring an opportunity or a risk? Are we happy that Maven's getting there a month before, or would we be happy or if it was a month after?
I haven't had a recent briefing, but the last time I talked to anybody, it seemed like everything was going to be okay. So the risk was manageable. And so once you say, okay, the risk is low, then it becomes a scientific opportunity, and it's really exciting. It's exciting in a good way, not exciting in a bad way. And I think that's where we are at the moment, that we're pretty confident that we're going to be in a good position.
Great, thank you.
Next.
Yes, my question is for Ellen and maybe Pascale and others to join in. And it surrounds how hard over you are for getting a soil sample returned to Earth before engaging in people on Mars and doing pioneering activities. Let's say for the sake of measurement, if you're of the opinion that it's not really necessary to have a Mars sample return, that you can maybe make some simulated Mars soil from Earth materials, but it's nice to have, you don't need to have it. Let's say that's a 1, all the way to a scale to a 10, where you say it would absolutely mandatory to have not only one sample, but many samples from around Mars that might cost $1 billion for every 5 or 10 pounds. And that would be necessary before you would even think of having a settlement activity on Mars. So if I could ask if you can put a scale from 1 to 10, where 1 is a nice to have and 10 is absolutely mandatory, where would you stand on that scale?
Obviously, from a scientific point of view, we wanted a sample from Mars, yesterday to understand more, obviously the mass specs we take up to Mars are this big, and the ones we have on Earth fill entire rooms, and there's a good reason for that. They have a lot higher precision. We can do much better measurements with them. So what we can learn on the surface versus what we can learn from actually bringing a sample back to Earth, there is a big difference there. I think there is a debate from a human toxicity environment point of view. Do we really need to bring it back before we send humans? Do we not? I'm probably at this point not convinced one way or the other on that. From a purely scientific point of view, I'm at a 1 or a 2 that the sooner we get the sample, the better. But obviously from an agency perspective, as we lay out this path to Mars and we merge the science needs with the exploration needs, I think the idea of utilizing a sample return mission to test out some of the capabilities that we need to land humans on the surface and return them safely to Earth, I would like to see a sample return mission folded into that, because to me it makes sense. But that's why we have so much work left to do, and the importance of meetings like this and the importance of bringing the community together and really discussing it is because, as Sam was showing earlier, there are many, many paths to Mars, and we have to find one that is safe, but that's also affordable. And I just think we're not there yet. We still have work to do.
Okay.
Yeah, I think I would agree in general. Mars sample return is for scientists a dream to really understand many, many different scientific issues when we bring back a sample and analyze it. I think before we bring human to Mars, we really need further robotic missions. That's clear, of smaller scale than Mars sample return, in order really to understand the risks. And I think what is most important is that we pull data together worldwide on all the kind of simulations which we do. There are worldwide many, many groups right now which are really working on the effects of perchlorates, which have now been found really ubiquitously on Mars, and what the effect is, not only on searching for life, but also for materials. And I think these kind of studies and many others, they have to be pulled together and worldwide, that we have a database and that we can move forward in addition to robotic missions which prepare for the landing, human landing.
Okay.
Can I add one comment here from a biology standpoint? If I was the first human astronaut to be on Mars, I would have wanted a lot of life science testing on real Mars stuff, as good as analogs are, for the potential long-term health concerns. And the dust that Joel mentioned. We've got good inferences of what the dust is like, but we don't have any of that real stuff to know just what the particle size is. A 1 micron particle is a bad thing in your lungs forever. That's an issue that would concern me that's separate from what we've said already.
Very good point.
Thank you.
Thank you. Next question? What about this side of the room? No question?
Sleeping.
Well, I'll try to make up for that with a couple of short questions. Hyperspectral imaging. Are there any orbital assets around Mars and any of the rovers on Mars that use hyperspectral imaging, and how well is Curiosity helping to make the correlation between what you see in orbit and what you can see on the surface, because calibrating your hyperspectral imaging with ground truth is kind of useful. And the second question, as much as we like to see sample return, there's also this question of fractional gravity. And looking, just off the top of my head, looking at the assets that have been in orbit for long-term testing up around Space Station, it strikes me that none of those assets were particularly expensive compared to the Mars Gravity Biosatellite, which has been designed, combination Georgia Tech and MIT designed. It's been put on the shelf and sitting there for about a decade. You can launch and test the mouse model in fractional gravity. And I'm sort of surprised that this has never been looked at. And just like sample return, this seems to be a very critical element. So I'd like you folks to rate the need for fractional gravity data and as well as discuss some of these possibilities of hyperspectral imaging. So go.
I'll comment on the hyperspectral part that we do have a wonderful hyperspectral instrument in orbit on Mars Reconnaissance Orbiter, CRISM. And it is opening our eyes immensely to compositional information. The individual CRISM measurements are on the order of 20-meter pixel resolution. Curiosity does not have what you would call a true hyperspectral capability, but it has a whole suite of things that can sample specific rocks and soil in a CRISM pixel and provide very crucial calibration for the CRISM team of exactly what they're...
That loop is closed.
Absolutely, and that's been going on since Curiosity began its investigation.
Also the Omega instrument on Mars Express. So,
Yeah.
part of the reason we chose that site was because of those two instruments that had given us this sort of hyperspectral data. So when Curiosity found clay minerals, the orbital instruments had told us that they were there. So we were able to confirm that with Curiosity and give that ground truth. And that, as you well know, that's so important because then you can say, okay, based on what we found on the ground on Curiosity, we can then calibrate those data and then have a much better idea of making sure we pick the next landing site even better than we did before. I'm not sure if that's proper English.
Thank you. I got my wish. We have a question from that side of the room.
This is probably mostly for Pascale. I've been trying to find more information about the result. I find a lot about what the experiments on Mars 500 were going to be, and I've had a very hard time finding data about what the results were and the analysis that's been done. Is that available online or elsewhere for the public, or like how would I go about finding that information?
You mean for Mars simulations? Or?
Yeah, for like the Mars 500 simulation specifically. I've had a very hard time finding information about the results.
I have seen some papers, and when you go on the website, you find a lot of detailed discussions about their daily measurements. It is true that there is one report which, when the mission was concluded, which which I looked at. New scientific results may still come out. I know that the main results have been coming out mostly through the press during the mission. It was a very, very highly press-attended event, and people liked it. It helped a lot for public awareness, I think, also in particular for future human missions. And there are some scientific papers which I have seen, which I can give you later.
If I could go back just a second, we forgot the fractional gravity part of your question. I think as we go forward in this process, which is obviously it's not a NASA process, it's a community process, it's an international process, it's a global process. of how do we make choices between now and if we're aiming for the 2030s, how do we make choices internationally within each nation's budgets of saying, what are the things we have to do? What are the things that would be good to do? And what are the things that are maybe a little more marginal? And how do we make those decisions as an international community? And that's obviously the importance of the global exploration roadmap and going forward, because no one can do it alone. No one has those resources. And I think as we go forward, you know, sample return, fractional gravity experiments, I think one thing that's really important is that we are able as a community to critically articulate what are the end kind of goals by which we are judging every decision we make for that path to Mars. You know, obviously landing humans safely on the surface and returning them is goal number one. But beyond that, how do you set up criteria so that as we make decisions going forward, we're using our international taxpayer dollars in the most efficient way forward to get to where we want to go. And human safety is critical, and I think fractional gravity is something we need to take seriously into account.
Just to follow up, are you folks aware of Mars gravity by a satellite as an existing object?
No.
And so when you look at that, it's fit to go on an Ariane. It's fit to park outside ISS and spin and put the little mice in there. It's fit to go to L1 or L2 or L something and combine mouse model with gravity and radiation. It seems like this is a little trade space, and it's probably less than Mars sample return by a lot.
By a lot.
You know, and so this seems like a trade space that ought to be in the thinking. So I just bring it up. I've pimped for this thing. I don't have a dog in that fight, but I've pimped for this thing 3 times at this meeting. I'm going to continue because I think it ought to be looked at.
Thank you.
Okay. Now, if I remember correctly, the lunar dust that showed up in the Apollo capsules was extremely abrasive and not only gave them eye irritation, also gave them lung irritation. Now, I think you may have worked around the edge of the question that I'm going to ask. But do we have a read on whether or not the Martian dust is not only abrasive, but whether or not it's toxic? Because if you breathe it for a couple of days and you start coming down with pneumonia, I don't think we're going to send too many people to Mars. Looks like we were going to skip the break, but then I am not aware of actual measures of tests
Other speakers in your
on that regard, but
Why not, Sheriff?
that was why I brought up the point about sample return. I think we need to get some actual Martian dust and characterize it in our labs here, as opposed to as good as our robots are, partly for the biological implications, because I don't think we know the answer to your question.
Well, I think it has been already discussed that in particular perchlorates and the chlorinated salts are toxic. They are difficult for the thyroid gland in humans. You have pulmonary troubles, which have been discussed. And I think something what I always read is that also the combination between dust and humidity involved in humans, that can lead to some rather complications, which is really not yet well investigated.
On the Apollo return, the dust that was on the spacesuits actually caused malfunctions in some mechanical systems on the way back to Earth during the 3 days. So it was very bad for mechanical systems. And remember, this is just the dust that was brought back on the spacesuits. Yes?
So following up on the sample acquisition question, how high do the dust storms or dust devils tend to reach on Mars? And is it possible we could use that to our advantage and have some sort of orbital platform that could take a sample of that and then send it back to Earth?
I can't, maybe Jim can give you a altitude level. I'm not sure what it is, but that mission's actually already been proposed before by Lori Leshin. It's, I think, called SCIM. SCIM. It was a Mars Scout mission that would dive into the atmosphere, take a sample that would presumably have dust. You know, dust in our atmosphere lofts extraordinarily high. I imagine it's the same on Mars. And to bring it back to Earth. So it's kind of a cheap and cheerful, if you will, sample return mission, and it has been proposed, and I'm sure I'm not supposed to say this, it's a really cool mission. So.
And in the first Mars Scout competition, it was one of the 4 finalists that eventually led to Phoenix being selected, but it was one of the 4 finalists.
In terms of altitude, the dust devils can immediately kick dust up to 10 kilometers, but the global dust storms can raise it to 50 kilometer altitude. And we have images and other measurements that demonstrate, yeah, the dust really does get that high.
So we just got to figure out those global dust storms and work on planning those out.
Yes.
Yeah. The Mars rover designers have their Mars yards at JPL and elsewhere, but these are very low fidelity simulations. And if I was designing airlocks or spacesuits or human rovers or whatever, I would want something perhaps on the order of the size of this room that had high fidelity simulation of the regolith, the temperature, the pressure, the insulation, the dust environment. Is there any plans to build such a facility?
I don't know. That's a good question. I've seen, I mean, we have a big lunar dust facility down at KSC. I don't think we can do temperature and pressure in it, but I think it's a great idea, and I don't know the answer.
I think that there are many aspects which are investigated, you know, concerning spacesuits, for instance. I investigated in Europe and the United States very much in detail about temperature and materials, contact materials, and also corrosives. So there is a lot of testing going on. Then you certainly know Pisces, which is really a large-scale operation in Hawaii, which is testing in particular for lunar exploration with rovers. It's a very large-scale, interesting program. So I think there is a lot going on. If there's exactly that what you asked, probably for Mars, but you know you can extrapolate and you can collect data for a lot of those individual. Pascale Lee was not here today. He would have told about these worldwide analog programs in the deserts, in Stofan Island, very much in the north, in Antarctica, where all those things are tested. And I think we have been discussing since a long, long time how to make an international analog test program, you know, in prospect and in support for future robotic and human missions. To Mars and also other destinations, and I think there should be a program which will be discussed probably also on the level of the International Space Exploration Working Group.
Any other questions? Well, I'd like to thank our panelists for their presentations and discussion. Thank you very much.